when we think about power supplies, when we think about regulators, we always think of them as, okay, that's a voltage controlled voltage source, right, and that the reference voltage is, so if I go back here, you would say that this is the, so let us say this is a voltage controlled voltage source, this is the controlling voltage, this is the output voltage, right. So, the controlling voltage is the band gap reference, controlling voltage multiplied by some gain factor is the source voltage. And when we say, okay, what qualifies a VCVS, you would say that VCVS typically means that output impedances right, input impedance has to be very high, but that we will not worry about. So, one of the things we associate with the VCVS is that it is low output impedance. It is not hard to understand, because you want to say that. So, let us say this is my I am not putting R out, I am putting Z out, because we are going to start looking at impedance as a function of frequency. So, it is important that we start thinking of it as impedance rather than just resistance. So, let us say this is the equivalent circuit. What we want is to be able to say that Z out should be low, right. Now, what does Z out should be low mean? We know R out. R out is the output resistance. Z out should be low is essentially saying that now, if I were to plot impedance as a function of frequency, right, I am hoping that across this entire band, right, across the entire frequency band, the output impedance will be low, right. So, need low Z out across the frequency band, right. So, let us try to refresh something we learned, a couple of things we learned in the previous chapter. So, when we say, okay, I have an amplifier, I will make it a simple amplifier for now. This is my amplifier. Or let's just, right. What is R out, right? We would say that, when I have an amplifier like this, let us go back to, let us say this division ratio is beta. So, R1 by R1 plus R2, let us say we call this beta, right. What would we say R out is? We would say that, oh, let me first calculate the loop gain. The loop gain is essentially A times beta, it is A multiplied by beta. Now, R out will be whatever R naught there is in the circuit. So, R naught might be the output impedance of whatever amplifier or transistor output path there is, and in parallel with R2 plus R1. So, R naught divided by 1 plus loop gain is the output impedance, right, of this feedback system. Now, loop gain is large. So, R out is small. This is the calculation we did, that because the loop gain is large, the output impedance will be small, right. Now, this is fine at DC. What you have to recognize is the loop gain is large at DC, which means that R out is small at DC. What happens to the loop gain as omega increases, right? Because if loop gain starts to reduce, what is going to happen? Loop gain starts to reduce, 1 plus loop gain is going to reduce. If 1 plus loop gain reduces, then the output impedance is going to increase, right? And it might be not R naught, it might be Z naught, but Z naught divided by 1 plus loop gain will start to reduce, will start to increase, because 1 plus loop gain is starting to reduce. So, now it is important, again we talked about stability, right. So, if you look at Bode plot where you are plotting loop gain, what you would essentially do is here, this is a simplified circuit, simplified graph. So, what you have the dominant pole and then you have a second pole somewhere where the phase before the phase can accumulate to 180 degrees, the gain has already gone below 0 dB, right. Now, this is the typical loop gain curve, and you would do this because you want second pole or loop gain should be less than 0 dB, 0 dB or the number 1 or less than 1 before we accumulate (180 degrees) of phase. So, that is why the second pole has to be located after the gain drops below 0 dB. So, now you can see that okay, from the dominant pole the loop gain is constantly reducing. So, suppose I were to go to a frequency here, right, which is maybe 10 times the dominant pole or 20 times the dominant pole, my loop gain or let us say it is 100 times the dominant pole, my loop gain would have dropped 100 times, right. What does that do to the output impedance? That becomes a question. So, now based on this, if you were to say okay, I want to plot the output impedance, you would, let us say let us choose a different color. So, let us also get this out of the way for a second. Let me just okay, let me just rewrite that here. So, loop gain drops below 0 dB or drops below 1 before phase reaches 180 degrees, right. So, now this is the Bode plot or the plot for loop gain. So, now say on the same frequency plot on the same x axis, now I am interested in plotting the output impedance, right. How will the output impedance look? What the output impedance will do is essentially start off low and then at this point start increasing, right. This will be Z out. Again, my curve drawing is not perfect, but you get the idea, right. Starting from the dominant pole, the output impedance will start to rise, because the loop gain is reducing, and it was the 1 plus loop gain factor that was really helping me. So, now if I were to use this, let us say somebody says, okay, you know, my bandwidth, which is this point here, this point, this is the bandwidth, right. Let us say is 100 kilohertz or 200 kilohertz, right. And then somebody might wonder, okay, what happens if I use this LDO for a digital application where my current is in the megahertz. You know, I am assuming this is a voltage source which will present very low impedance at high frequencies, right. At DC is okay, but my load current has a certain frequency nature to it, and what will happen to the performance at those frequencies, because if the output impedance is very high, then I am going to get a lot of voltage drop at that frequency, and that is going to have its own associated problems, right. So, the question now becomes, you know, how do we keep Z out low across frequencies? Because if your Z out is not low across frequencies, then so let us say Z out is not low across frequencies at the point or at the frequency where now your block might consume current, your block will have a certain current signature, which means it has components of current spread across different frequencies. That current has to come from this LDO only, and if the output impedance of the LDO is very high at some of these frequencies, you are going to see a lot of voltage drop at those frequencies. So, to avoid that, we need to keep Z out low across frequencies. So, how do we do that? One component that we are familiar with is this, is the capacitor. How does the capacitor's characteristics look as a function of frequency? So, now if you were to plot impedance as a function of frequency, a capacitor would do, so again pardon my curve, but the capacitor will do something along this line. So, this will be 1 over omega c, 1 over j omega c, we are talking magnitude of the impedance. So, 1 over omega c, right. So, one case you can make is to say that, okay, I am just going to put a large capacitor at the output, and if I put a large capacitor at the output, anyway that is going to make sure that as I go to higher and higher frequencies, the impedance is going to drop, right. Sounds very good on paper, but what you might be surprised by is that you know, something that we said in an earlier lecture as well, in the world of electronics, it is important to know that there is no such thing as an ideal component, right. Every component will come with non-idealities, and it will also come with variability. In this context, we are interested in the non-idealities. So, while we look at something like this and we say, oh, okay, you know, all right, this is my problem, I am going to put this, I am going to put a large, they said 1 microfarad capacitor, I am going to put a 1 microfarad capacitor and I am done, right. Now, this is my circuit diagram. So, right. So, now if I were to let us try to let us say I am now plotting Z out as a function of frequency. The amplifier might do this, but the capacitor does this. So, now the output impedance, so this is just the amplifier, and this is the 1 microfarad capacitor. So, you can argue that, okay, now what is going to happen is the output impedance will do something like this. This is the Z out effective, right. suppose you were to come up with this analysis and say okay, problem solved, right. Right. Now, if you were to do this analysis and say okay, problem solved, you would be surprised to find that your problem is not really solved. You would be surprised to find that okay, Z out effective started off lower, but then what happened was, so while this is your expectation, what will likely happen is that your Z out effective will do this and then start so this is Z out effective actual and this is Z out effective expected. Now, you do this and you might wonder, but why is this happening, right? This goes back to whether components are ideal or not. So, when you look at a capacitor, right. So, let us say I have a surface mounted capacitor. Now, the surface mounts have leads have inductance, etc. So, let us say this is a 1 microfarad capacitor. This 1 microfarad capacitor will have an equivalent circuit that looks something like this. So, this is the inductance and so there is inductance and then there is resistance of the lead, right. So, what they do is they lump these together. So, there is the effective series inductance, there is the effective series resistance and then the intended capacitor of 1 microfarad, right. So, this is actually the equivalent circuit for a surface mount capacitor. Now, let us say a surface mount capacitor has this equivalent circuit. Let us put some numbers also. This maybe is 0.1 ohm and this maybe is 100 nanohenry, right. Suppose this were the effective series resistance and effective series inductance, how would the characteristics of the capacitor look, right. So, now if I were to plot again as a function of frequency the impedance of the capacitor. So, let us say looking in here, this I call ZC, this I ground, right. This looking in impedance I am calling ZC. What ZC will do is it will initially it starts from at low frequency is all in series. So, whichever is the highest one dominates. At low frequencies it is going to get dominated by the capacitor. At high frequencies it is going to get dominated by the inductor, because inductor goes as 1 over omega c, and at some frequency because of the series combination of the inductance and the capacitance, there is going to be resonance. So, what is going to happen is that you will see something that looks like, so it is doing this, then it resonates. So, this is some, again pardon my drawing skills, but what you will find is that the impedance will drop all the way to the effective series resistance at the self resonance frequency. So, self resonance frequency will be 1 over 2 pi root of LC, right. At this frequency it will have resonance. You know the inductance and the capacitance, so you can calculate this frequency. So, at 1 over 2 pi square root of LC is where it will resonate. So, in this case it will work out to be close to a megahertz or so, right, maybe slightly higher, but somewhere in thereabouts, right. And then the impedance will start to increase, right, and it will increase. So, this here it is now dominated by the effective series inductance. Here behavior determined by the capacitance. So, it is important to understand that your capacitor behaves like a capacitor only as long as the frequency is less than the self-resonant frequency. Once the frequency is greater than the self-resonant frequency, it starts to behave like an inductor, which means that its impedance is going to keep increasing with frequency, right. If you were hoping that okay, I will put a 1 microfarad capacitor, my job is done, that is really not the case. What you will find is beyond, let us say, the self-resonant frequency is about a megahertz. Once you cross a megahertz, the impedance will start to increase. So, if your circuit or if your application, let us say your MCU has current at 10 megahertz or 20 megahertz, where that is where the most of the power is, or that is where most of the current is, then you will be surprised by the amount of voltage drop you get at 10 megahertz, and you might be scratching your head wondering, no, I put a capacitor, why is this not happening? So, this is why you might not get a good impedance. Now, the question becomes, okay, is that all there is to it? Can I do nothing about it? No, there is something you can do about it. What you can do is say that, oh, okay, if I put a 1 microfarad capacitor, then maybe this is the self-resonating frequency. What if I put a 100 nanofarad capacitor? What if I put a 10 nanofarad capacitor? So, if a 1 microfarad, let us now go back here. Let us let's go back here. So, when we think about okay, we have the 1 microfarad capacitor, we have to accept the self-resonant frequency of the 1 microfarad capacitor. We can say okay, if we have to accept the self-resonant frequency of the 1 microfarad capacitor, can we think about using a smaller capacitor that. So, now let us go back to the amplifier did something like this in terms of its output impedance. What we just learnt is a 1 microfarad capacitor, right, does something like this. Again, pardon my drawing, but you get the idea. So, now you can say okay, if a 1 microfarad capacitor does this, what will a 100 nanofarad capacitor do? So, a 100 nanofarad capacitor, for example, will be higher here. So, it will do something like, wait, I should 100 nanofarad capacitor will do something like this, and then a 10 nanofarad capacitor will do. Now, the characteristics are all the same, right, they all have self-resonant frequencies, but because the capacitance value reduces, the self-resonant frequency keeps moving, right. So, this is now SRF for a 10 nanofarad, this is SRF for a 100 nanofarad, and this is SRF for a 1 microfarad capacitor. Now, if I were, for example, to now put, let us say I play with my circuit now, I say okay, I am going to not stop at one capacitor, I am not going to stop at one capacitor, I am going to put one 10 microfarad or I am going to put one 1 microfarad capacitor. In parallel with it I am going to put a separate 100 nanofarad capacitor. In parallel with it I am going to put another 10 nanofarad capacitor. Suppose I now build it up like this, what will happen is the equivalent impedance now will start to look something like, again it might have some undulations, but it might start to look something like this, right, where eventually it approaches the characteristics of the 10 nanofarad capacitor, but now over a much wider frequency band I can maintain a over a much wider frequency band I can now maintain a low impedance. So, essentially by recognizing that capacitors have self resonant frequencies and higher the capacitance lower the self resonant frequency, I can now think of an array of capacitors at the output of my amplifier that allow me to maintain a low impedance across a larger frequency band. So, now if my digital logic has a high component of current at 10 megahertz, I do not have to worry about it so much because I have a 10 nanofarad capacitor that is protecting me for that frequency, for current at that frequency. If I had high current at 300 kilohertz, maybe my 1 microfarad capacitor steps in and ensures that the impedance is low. So, I have essentially chopped the frequency domain into different bands and said each of these bands is now the responsibility of one of these 4 guys. So, first the amplifier takes care of very low frequencies, it gives me low DC impedance, it takes care of very low frequencies. Then the, then the 1 microfarad capacitor kicks in and says okay, let me extend that frequency band a little bit through my capacitive action. And then the 100 nanofarad capacitor says okay, we have hit the self resonant frequency of the 1 microfarad, but I am still behaving like a capacitor, maybe I can take some of the load. And then once it hits its self resonant frequency, the 10 nanofarad capacitor can do the same, where it says okay, 100 nanofarad capacitor self resonant frequency is also hit, but I am still functioning as a capacitor. So, we can maintain a lower impedance over a wider frequency band. Now, it might so happen that the chip itself has about a nanofarad of capacitance. Nanofarad is large, but it is possible if it is power intensive like a microcontroller, it is a reasonable chance that there is local decoupling on the supply in the chip. So, it might so happen that while the LDO does all this, you might get help from the chip where the chip has a 1 nanofarad capacitor which, so this is maybe it is very light, sorry, let me take a darker color, running out of colors here, let me see, olive maybe. So, the chip might have a 1 nanofarad capacitor. So, this might be a 1 nanofarad cap on the chip. So, this allows us to extend the, in which case now the output impedance will get extended even more before it starts to rise, right. So, by using an array of capacitors, it is possible to ensure that we get the kind of output impedance profile that we want. Okay. So, please keep this in mind, when we look at when you look at other schematics, you will notice very often you will see this configuration, right. If you see this configuration of capacitors, bear in mind that it is done to extend a low impedance across a wider frequency, right, very commonly used trick, and the logic also is simple. So, here again you should look at the data sheet of the capacitor to get a sense of what its self-resonant frequency is. Now, some capacitors are rated for 3 volts, some for 6 volts, some for 25 volts. Higher the capacitor rating in terms of voltage, usually lower its self-resonant frequency, because it is adding more and more layers of protection. All of that adds to the non-ideality of the capacitor. So, it really functions like a capacitor only up to a small band. So, if that is the case, then you might again need to revisit how you sequence this array, right. So, this is about the stability of the linear regulator. So, bear in mind that the loop gain for any amplifier will drop with frequency. As the loop gain drops, the output impedance will start to increase, and that has to be counteracted by something, and that something is the array of capacitors. One capacitor is not enough, because beyond its self-resonant frequency, it no longer functions like a capacitor, it starts to function like an inductor. So, it is important for us to have an array of capacitors if we are particular about maintaining a low output impedance across a wide band of frequencies.